Welcome back to chemistry, everybody. Today we are going to be talking about light and how it is created. So we already know some of the different equations for light. We know what wavelength is and frequency. We've got all these different pieces of information. Now we need to actually just see how light comes to be. We know that it's not matter, it's actually energy, but what is creating that energy that allows us to see? And so the way that we explain this is through atoms. It's atoms that actually create light. And we explain this using one of the scientists that we talked about the other day in the history of the atom. We talked about Bohr. And Bohr came up with a model of the atom that described energy levels in something. So that's what we're going to kind of take a look at today. So a couple of things. First off, because atoms are what are responsible for creating light, we can actually identify atoms by the light that they produce. This is how we know what our sun is made out of, right? Our sun is mostly hydrogen and helium. How would we know that? We can't actually go to the sun or send a probe there, but we can look at the light that it produces. So the way that we identify these atoms by the light that they emit is what we call the atomic spectrum. It's almost like every element has their own fingerprint. So when they produce light, they don't all produce the exact same colors of light. So the way that we do this is we basically take the atom in their pure form and take a look at the rainbows that they produce. The rainbow is what we call the emission spectrum or the atomic spectrum. Those are kind of interchangeable. So in order to get the rainbow, there's a lot of different ways that you can get a rainbow to form. Some of us have seen rainbows using like 3D glasses or the back of a CD or a DVD. We call these diffraction gratings. You could also use something more expensive like a glass prism, but we know that water droplets in the atmosphere produce rainbows all the time. And the idea is in class, the way that we do this is something called a spectroscope. So let me show you a spectroscope real quick here. This is a spectroscope, and when we look at the spectroscope, basically that little piece of plastic that is in 3D glasses, you can kind of see the rainbow that we're starting to get right there in the little opening in the little eyepiece. Okay, so that's what we call a diffraction grating. And then on the other end, there's a little slit that allows the light to come in. And then this isn't really 100% necessary. What this is, if we look really close, I don't know if we can see it, there's numbers on it, so that when we look inside, we can actually see the wavelengths of the different colors that we are producing. So if I hold this up to the camera, so maybe we'll look up at the lights here. I'll do my best to put it up to the camera. You can see when I put it up there off to the left, it's not focusing super well, but we can see all those numbers. We can see the exact wavelengths of the purple and of the, the green and the red and the orange. All of these different colors are showing up. Now you'll notice that all of the colors are here because I'm kind of pointing it toward the windows, or even if I point it up directly above my head toward the lights, it's got all of them. These are what we call full spectrum lights, and they're basically covering a lot of different elements and a lot of different wavelengths. Now if we want, we can get atoms in their pure form. So if we look over here, this is basically like just a lamp. And plugged into that lamp, I have a bulb, and the bulb has hydrogen in it. And it's pure hydrogen, basically. So let me shut off the lights really quick so that we can get a good look at it. And I'll flip this on, and we'll see what hydrogen in its pure form looks like. So if I turn this on, we can see that we get kind of I don't know, it's like a reddish purple color. Now what we're gonna do is I'm gonna do my best to try and let you guys take a look at what the fingerprint for hydrogen looks like. So I'm gonna go ahead and I'm gonna try and get this up here. It's not the easiest thing in the world doing it through the iPad, but let me see if I can It's not showing me what I want here. Where are we at? Okay, we're starting to get some here, but it's not quite what I want. Line up, line up. That is... Get on the scale for me, you stinker. It's not showing up great. If we look off to the right, we can see them showing up better over there. I'm missing a big giant piece of it, though, on the left. But if we look at the right, look over at the right, you see that the blended colors are there, but you see 3 sharp lines standing out even more. There's a sharp red line, there's a sharp sort of blue-greenish line, and then like a sharp purple that's pretty faint, but you can see it kind of coming and going. If I could get this lined up better, I could get those over the actual scale. But hydrogen has 3 lines. The rest of that blended background is light coming from heat off of the bulb and through the windows, so it's not ideal. But that would be our hydrogen bulb. Let's try a different element. So we'll shut that off, and we'll try helium next. So let's see. We've got that. Let's go with helium. Okay, so we'll flip that on for helium. Helium is more of like a yellowishy kind of peach color. So let's see what we can get. Now, once again, look off to the right. You see it a little bit better. The number scale is kind of popping up. Very hard to line up. Where are you at? There, it's popping up really well off to the right. We have a red. We have that orangey yellow. We have almost looks like 2 blue-greens and 2 like purpley blues. So it's a very different spectrum for helium than it is for hydrogen. So it's on the wrong side here, the way that it's moving through my iPad, but we could see the spectrum is very different for hydrogen than it is for helium. Let's try another element. So we shut that off, and let's go with another one. Is a common one is neon. We've all heard of neon lights. You go to Vegas, you see everything up in neon lights. Neon is not the color that everybody thinks, right? What color is neon? Well, if it's a real neon bulb, it's not blue. Neon is super bright and it's super orange colored. It's sort of blurring out all over the thing here. But let's take a look at what the spectrum for neon is going to look like. So if we get this up here, let's see. Where are you at? Having trouble. I might not be able to get this one. There we go. Am I just in the wrong? Whoa, there it goes. Look off to the left or the right. It looks like it's kind of popping up in both places here. Neon has a lot of colors, but do you see it's kind of blurring through the iPad. It doesn't do this when you look at it with your eye. It's just so bright. Can you see how many little red lines there are and how many little orange and yellows? They're stacked up on top of each other like crazy. And if you get enough of them, they start blurring together. But when you look at this without the iPad, they don't blur together, and you see so many sharp little distinct lines that we see neon is very, very different. So every element is going to look a little bit different, and we say that every element has that atomic spectrum. So they actually plot these, right? So hydrogen we saw, for us it really only had 3 lines. That's what we saw. And then we saw helium had more, right? It had that yellowy color in the middle with the red, and then we almost saw like a couple of like bluish purples and maybe a couple of greens. We didn't see all of these little ones through the iPad, but we did see a couple of blues and then a couple of blue purples. And so we see they are all very, very, very different. And this is what we say, once again, we call the atomic spectrum. Now, Bohr is the one who explained this. Bohr is the guy responsible for explaining what's going on here. Bohr basically said that the atom produces light by its electrons moving around. So when the electrons move farther from the nucleus, it has more energy. The atom is almost acting like a battery. You charge it up, and then when it relaxes, it releases its energy, and it comes back out. So we have some terms. We have ground state, excited state, and ionization energy. These are terms that we have to know. Make sure that you guys write them down. Now, I'm going to explain these by actually looking at a model of the atom. Remember what Bohr thought the atom looked like. Bohr said that we have a nucleus in the center, and then there are these rings that go around it, right? So if we were going to draw it, it would look something like this. There's our nucleus, and then there's a ring here and a ring here, and it just keeps getting bigger and bigger and bigger, right? And he called this n equals 1, n equals 2, n equals 3, n equals 4. That's a 4. These are what he called energy levels. So something way out here, the electron has to have a ton of energy. Because remember, the nucleus is positively charged and it's pulling on a negative electron. So in order to get this far away from the nucleus, it must have a lot of energy in it. If it's really close, it doesn't have very much energy. So the idea is the electron starts close to the nucleus. That's its home. That's what we call the ground state, where it normally exists and where it belongs. Then I plug it into the light socket and electricity goes in, right? The electricity is going in with the form of heat, really. And heat is energy. And so this electron absorbs that energy. And if it has a ton of energy, it can move farther away from the nucleus. This is the equivalent of charging up your phone or a battery, right? The electron orbits a few times, right? It's flying around out here at this high energy state, but what goes up must eventually come back down. When you turn your phone on and light comes out of the screen, the battery starts to go dead. That's the same thing we have happening. So eventually this high energy electron says, no, I'm going home. I've had fun out here, but it's time to go home. So it'll drop back down, and when it falls back down, the energy that went in as heat will come out as light. All right, so we're basically converting one energy to another. And so we know that we have some equations. We have E equals HV, right? And we know that frequency is basically the color of our light. And so the energy, right, the more energy that's released is going to determine the color. So if we look at this element here, maybe the electron just fell a small distance. Well, when we talk about colors, remember Roy, G, Biv, right? Red, orange, yellow, green, blue, indigo, and violet. These guys are low energy, and these are high. So if it only falls a little way, it's releasing a low energy, which might be red. If it falls a really, really, really long way, that's a high amount of energy, might be blue or violet or something like that. So the farther the electron falls, the higher the energy and the more toward that end of the color spectrum we have. Now, if I add too much energy, remember, if I add a little bit of energy, it goes up a little ways. If I add a little bit more, it goes up even more. Well, I can add too much, and the electron not only just goes up, but it takes off. If that happens, my atom is now going to have a missing electron, and we have a plus charge that has formed. So you have something like calcium with a +2. You put so much energy in that 2 electrons flew off of the thing. That's what we call ionization energy. We put so much energy in that it became an ion, and we end up with a cation, a positively charged ion. So when we're looking at light, that's the short of it. You add energy, the electron goes up. When that electron gets tired and falls back down, it releases it in the form of light. The farther it falls, the more energy that comes out, and the higher energy color that we're going to be seeing released. So something like hydrogen, if we look at hydrogen, it only has one electron. So your electron doesn't have a lot of options for the colors it could make. So we saw that it only had 3 colors, right? But when we went to something like helium, helium has more electrons, and we saw more like, 4 or 5 bands of color for helium, right? The more electrons you have, the more options that you have for these things falling. They can go up higher, fall further down, right? You just got more combinations. More combinations give you more bands of color in your atomic spectrum. Now, electricity is not the only way that we can produce this. We can produce this with heat in any form, not just electricity. So let's take a quick look at that. All right, so we know that we can use heat in order to add energy to a different atom and excite the electron, allowing it to come back down. But the heat is just a form of energy. We're just putting energy in. We have other forms of energy, right? Some of these forms of energy that we have are things just like flashlights, right? So you can turn on a flashlight, and the light itself that comes out of the flashlight is a form of energy. Now, the light that's coming out here, visible light, is typically not high enough energy to actually do any kind of exciting of the atoms. Like when I shine this on here, it's not glowing. We need a higher energy form of light. And when you remember the spectrum, remember that we have infrared, and then we have the visible light, and then finally we have the UV light. UV light is a higher energy light, higher than blue, right? It's ultraviolet, it's past violet, and it's got enough energy to actually burn our skin. So when we're looking at these, we see some of the things that I have here. I just took some water from the faucet and I put it here. Then I have some tonic water. You can get this at the grocery store, tonic water. Eosin Y is like an additive that they put in certain things. This is a yellow highlighter. What I did is I just took some water from the tap, and I took a highlighter, I took the cap off, and then I just dropped it in and I let it soak for a little while. And so some of the highlighter chemical came out. And then I just took some like regular like food coloring that you would put into something. Now, to make this a little more visible, we'll see that some things are able to excite at these lower energy levels, and some things are not, right? Some atoms are more complicated, they have more electrons, and there's more difficulty. You need higher energies to excite. Maybe it takes something really high energy like heat, and some don't. So let me turn the lights off. I'm in the stock room here. So when we turn the lights off, we see that the camera's having a hard time viewing them now. And so I'm going to go ahead and switch to a black light. So on this thing, we've got the black light here. And basically what a black light is UV light, okay? Now, it's the higher quality bulb you have for a black light, the more pure it is in terms of just being UV light. Because this is a cheaper one, we see a little bit of the purple. The idea is when you have a bulb, it's a mercury bulb, and mercury has a full spectrum of light. That's what basically a fluorescent bulb is. But in addition to that, they also produce UV. So like if you have one of those like twisty, spirally bulbs in your lamps, they are actually releasing some UV light. And so what they do is they paint the bulb black, and it absorbs all of the visible light, but the UV light can still come through. So let's take a look and see how UV light is reacting with some of these different chemicals. So let's start with, say, the water, and we have that in the form of tonic water, and we also have it in the form of the just plain old tap water. So when I bring the UV light next to these, you'll see that there is a chemical in the tonic water. So if I hold it behind the water, we get kind of that bluish color. We get the same with the tonic water, but we can see that it's very different, right? The tonic water is literally glowing. just the color of the UV light is this one right here. But this is literally glowing. The energy that is coming from the UV light is causing the electrons in this water to excite and relax back down. Okay? Now let's compare that to some of those orange ones, like the food coloring. So this one is food coloring. And so the food coloring doesn't really give us much, right? It's pretty dark. But we set that next to the other, and we see that that one lights up completely, right? So when that UV light is going into this bottle, electrons are being excited. And when they drop back down, they're not dropping as far, right? UV light would be a really big drop. So they're going really high up, and then they're dropping little bits of the way, and they're releasing more of a yellow color, which we know is more in the middle of the spectrum with regards to color. And then the last thing is actually highlighter, the highlighter. So we put the highlighter there, we see that highlighter is really, really good. This is why highlighters are so bright to our eyes, because they are literally glowing on the page, right? So I took a highlighter and I wrote on a piece of paper, and you can see that when you hit this with the UV light, it literally is glowing. The atoms are having their electrons excite and fall back down, and this paper here is actually releasing light, not just reflecting it like a lot of colors that we would see from regular markers. And so we put these in lots of different things. Chemicals that will take UV light and absorb it are known as phosphors, and we add them to all the different colors of highlighter that we have out there. They actually add it to laundry detergents, right? You watch a Tide commercial, they say, we make your whites whiter and your brights brighter. Well, the reason that your whites literally are glowing is because they are literally glowing. When you have an old shirt and you go to like a haunted house or something, old shirts glow really, really, really well. It's not just because they're white, it's because they have had years of laundry detergent that's absorbed by the fabric. If you have a new shirt, it doesn't glow. This is why, right? Think about this. Your eyes, you have whites in your eye. They don't glow in a haunted house, but your teeth do. Why do your teeth glow? Well, they should. Why do your teeth glow, but not your eyes? They're both white. Well, you brush your teeth with Crest or Colgate, those types of things. And some of the chemicals that are in those toothpastes are phosphors. And your teeth have absorbed them. And so they are literally making your teeth glow when you smile outside, because you're getting UV light from the sun, you're getting UV light from the lights overhead. So something to keep in mind there. Heat is one way, but we can also use light. It's just not everything works with light. The light needs to be a little bit higher energy than usual.